about the fundamental theme of calculus, which is one of the important themes in calculus. Okay, so I want to get this done. Okay, cover this. So suppose we have a continual function on this closed interval AB. Okay, this integral here, you can try to imagine that as the area under the curve. Okay, try to visualize this way. If it's a positive function, think about this area under the curve. Okay. Now, the integral of this continual function, x here go from a to b. Okay. Now, notice that x over here is this variable that it can replace by other variable. Okay. So if I replace the x here by t, that will be the same. These two integrals are the same. Okay. So because you're having the same function and you're integrating the same function from a to b. Okay. Now over here, if I let x to be any number that's between a and b on this interval, now I reserve this x here as this number here between a and b. To represent the area under the curve from a to x, there'll be the integral of the function from a to x. Because I use x here, I don't put an x over here, okay? X is reserved for this upper limit over here. Now, you can think about this as the area so far function, okay? Think about this. So when you move this x over here, this area under the curve is going to change. So this is a function, okay? It's the area function. Area so far function, okay? From here, so far, this will be area. We can label this function over here. It is a function of x, okay? It changed, the area here changed as this x here changed. So we call this function g of x, okay? Okay, now let's use some simple example to help to understand this, okay? We're going to discover this fundamental theme of calculus. We're trying to get some observation on that, okay? So I have a simple function, f of x equal to x, okay? Well, which is the same as ft equal to t, okay? So the graph of it is a straight line. When we integrate this function from 0 to x, okay, what happened over here is this corresponds to the area under this graph right here, okay? T here go from 0 to x. Think about this integral as this area right here, okay? So we know how to find this area. This is just a triangle, okay? So it is 1/2 times base times height, okay? What is the base over here? Anyone?
X.
X, yeah. The base over here, it is x, okay? And what's the height?
2 times x.
2 times x, okay? That's f of x, that's 2 times x, okay? That's 2 times x. So simplify this become x squared, okay? Which is a function of x. So when you move this x from 0, maybe keep on moving to infinity, then this area is going to change as this x change. So indeed, this area here corresponding to x squared over here, which is a function of x. Now, what happens if I see, so I integrating this function f from 0 to x. I got x squared, right? Okay. Now after that, I'm going to differentiate this function with respect to x, okay? So let's differentiate this function with respect to x. What do you end up with?
2x.
2x, right. You got it, 2x, okay? And you see what happened over here. This function that you end up with over here is the same function that you integrate with in the beginning, okay? It's just a different variable. It's actually the same function. So ft equal to t or fx equal to x is the same function, okay? So you see that it kind of observe this, okay? So integrating this function, continual function from a constant to x, later on differentiate that function with respect to x, you end up with the same function that you start with, but you just use the x over here replaced by the t. It's the same function, okay? Now let's try another example. This time, we're going to integrate this integral from 1 to x. So this is the function, this graph of the function, ft equal to t. We integrate this function from 1 to x. So think about it as the area under the curve from 1 here to x over here. So this looks like a trapezoid to you, right? Do you remember the area for trapezoid? It is 1/2 the top base plus the bottom base times the height, okay? So 1/2, okay? So the top base is this one, which is 2, okay? So that is 2. What about this bottom base here, the purple one over here? What is it? This is x, right? So what will be this?
2x.
2x, yes, you got 2x. And then what will be the height? Height, this is a height for the trapezoid. What's this height?
X minus 1.
X minus 1, you got it. So that will be x minus 1, okay. X minus 1, okay. So the y coordinate subtract the left coordinate give you the distance of this nice segment, okay, x minus 1. Divide out by 2, so this divide out, okay, so you have 1 plus x times x minus 1, which is x squared minus 1. So we get a function of x, right? You see, when you integrate this continuous function from 1 to x, you get a function of x. Let's write down the result. So we got x squared minus 1, okay? Let's call this function g of x. Now we're going to differentiate this function, g of x. Differentiate that with respect to x. Then what do you get?
2x.
2x.
2x, right? Yeah, good. Okay. Now, do you notice that this function that you end up with is the same function that you integrate with in the beginning, okay? So over here, we observe that if we integrate this continuous function from a constant to x, we end up with a new function, and then we differentiate that with respect to x. Then we get back to the same function that we integrate with. So you see this integration and differentiation here is kind of like the reverse. They are reverse process, okay? So they cancel out. So it's like you put on your shoe, okay? And then you take out your shoe, okay? Then you didn't do anything. You end up at the same position, okay? So you go forward one step, and then you go backward one step. You end up with the same place, right? So over here, integration and differentiation here, you see that they are reverse process. So if you integrate the function from a constant to x, and then later on differentiate that with respect to x, you end up with the same function, except that you just need to replace this t here by x, okay? Okay, so that's the observation, right? Okay. Okay. You get back to the same function that you start with, okay? So this is actually the Fundamental Theorem of Calculus part 1, okay? So that's what this is about, okay? So it says that if you integrate a function, say a function f is continuous on a to b, or this closed interval, then if you integrate this function from a constant to x, later on differentiate that with respect to x. Remember this symbol here means you differentiate with respect to x, okay? Then you end up with the same function that you start with, you integrate with in the beginning, except this time you just need to replace the t here by x, okay? So that is a Fundamental Theorem of Calculus part 1. Now, we just observed that, right? We didn't prove it, okay? The proof of that is on page 388 to 389, okay? So the proof is in the book. Okay, now let's try to find the duality of this function. This function is defined by this integral, okay? So basically, I'm differentiating this. So I'm differentiating this function with respect to x over here. So by the Fundamental Theorem of Calculus part 1, okay, let's call it FTC, Fundamental Theorem of Calculus part 1. So when I say part 1, that means there's a part 2 coming, okay? So this is part one, okay? So according to this fundamental theorem of calculus, part one, when I integrate this function from a constant to x, when I integrate this continuous function from a constant to x, later on differentiate that with respect to x, what do I end up with over here?
Probably we need to substitute all the t's for x.
Yeah, so you end up with the same function that you start with, except this time you replace the t here by x. Yeah, you got it, okay? So you will replace this t over here. So replace the t here by x, okay? Okay, the same function you start with. Okay, now the next one, Presto function, okay? Now this function here is used in statistics, physics, and chemistry, okay? So this function is defined to be this integral of this continuous function, okay? Now we're trying to find the derivative of this function with respect to x, okay? So by the fundamental theorem of calculus part one, what do I end up with here?
The same function.
Same function, yes. Okay, except you just need to put the variable here as x, right? Because it's a function of x. Yes, we got it. Good job. Okay. Okay, now the next one. This function over here is the integral of this function from 1 to x to the 4th power. Okay, notice that it's not just x. Okay, so and then later on differentiate this with respect to x. What do you think it's going to end up with? You can take a guess. Well, let's investigate on this, okay? So this is not just x, okay? How about if we let that to be a single variable u, okay? So let u equal to x to the 4, okay? Now remember, this is a function of x, okay? So y over here, okay? So if I let u to be x to the 4 power, then this y over here is a function of u, and the u over here is a function of x, okay? U equal x to the 4, right? So u is a function of x. Y over here is a function of u. If you think about this as a single variable u, okay? Now, when I differentiate this y, right, with respect to x, so dy dx, okay? Dy dx. So dy dx, according to the chain rule, that will be equal to dy du times du dx, right? Remember the chain rule, okay? So it looks like you can try to remember like this to cancel, kind of like that, right? So that was the chain rule, okay? So this dy dx over here is dy du times du dx, okay? So dy du, okay, y is this whole integral over here. So we write down, so it's this integral from 1 second of t dt from 1 to u, right? Okay. Okay. And u over here is what? U is x to the 4 power, okay? So put x to the 4 power over here. The y is this integral, so I just copy that down. Now this part here, we know what to do, okay? So we integrate this function, continuous function. So we integrate this continuous function from a constant to u, and then later on differentiate that with respect to u. By the fundamental theorem of calculus part 1, what do I end up with over here? You can enter in the chat.
Secant u? Is this secant u?
Secant u, you got it. Okay, so secant u. Okay, so we end up with secant u over here. So we get secant u. Okay, but u is so let's put
X to the 4th.
x to the 4. Yes, okay. So later on, we can replace this u back by x to the 4, right? Okay. Now, times the derivative of x to the 4 with respect to x is equal to what? What's this?
4x to the third power.
You got it. 4x to the power. Okay. Okay, now we need to return back to x. So we place this u here back by x to the 4 power. So we got secant of x to the 4 power times okay times 4x cubed over here. Okay, all right. So now we can have a shortcut. Okay, so after all this, we say you don't have to go through this again and again. So there's a shortcut. So basically, you're going to get, okay, so what's the shortcut? So basically, you get back to this function over here, secant, okay, secant, and then secant, so secant of, where is it? Okay, so we're going to replace this x to the 4 here by, replace the t here by x to the 4, okay? So you take a look over here. So if we, so what do I have over here? 1, and then this is x to the 4 power, right? Okay, give me these different colors. So x to the 4 power. And then this is what? Secant of t, and then dt. And then now we differentiate this with respect to x, right? Okay. Then the derivative of that, okay, the derivative of this, you see this part over here is equal to this, and you can see the pattern, right? So basically, you replace this x to the 4 over here, okay? No, basically you replace the t over here, right, by x to the 4, okay? You get this function right here. And because this is not x, this is a function of x, okay? By the chain rule, we have to multiply by the derivative of this with respect to x, which is 4x cubed over here, right? Okay. So you see the pattern, okay? So that's a shortcut, okay? Okay, now let's try this one over here. We can try to use our shortcut this time, okay? So when I integrate this continuous function from 1 to square root of x, later on differentiate that with respect to x. So what will be the derivative of this function with respect to x? Anyone?
So we got two parts. The first part is the same function, but we replace it with square root of x.
Yeah, you got it. Okay, and so we place the z here by square root of x. Okay.
And then
by the chain rule, we multiply this by the derivative of square root of x, right?
Mm-hmm.
Okay. The derivative of that. Okay. Okay, now let's simplify this. That's equal to, this is x, this is x squared plus 1, right? Okay. And then times square root of the derivative square root of x. Do you guys remember what is it?
It's 1 over 2 times square root of square root of x.
You got it. Okay, good job. 1 over 2 square root of x. Now, remember this x here is the same as square root of x times square root of x, right? So one of them is going to divide out, Okay, so divide out over here. Simplify, you get square root of x on top over, okay, there's a 2 over here, parentheses, x squared plus 1. Got it? Okay. Now it looks so complicated in the beginning, but once you break it down like this, it's actually not too hard, right? So yeah, don't be intimidated by those symbols, okay? Okay, now let's try this one. Now this one over here, we integrate this function, continuous function, but it's not from a constant to a function of x. Instead, it has a constant up here and the function x down here, right? If you try to find the duality of this with respect to x, we like to switch them. It has to be the constant as the lower limit, okay? So we want to switch them. Okay, and put, so we want it to be in this way. So we want to have 1 down here and then sign of x up here. What happens if you switch the upper and lower limit? Remember the property for definite integral? When you switch the upper and lower limit, you get opposite, right? So we have to put a minus sign in front. So put a minus sign over here. Okay. Now this is better. Okay. Now we have integral of this function from a constant to a function x. Now we're going to differentiate this, okay, with respect to x. Now the minus sign over here, when you differentiate this sign here, just copy over here, right? So just copy. Now we're going to differentiate this with respect to x. Use the fundamental theorem of calculus together with the chain rule. So what do you get, everyone?
Cosine of x times the same function, but
Yes.
we plot sine of x in.
You got it. So you're going to replace this t over here by sine of x first, right? So square root of 1 plus the square of sine x, okay? Replace t by sine x by the chain rule, okay? So times, so by the chain rule, okay? We have the times the duality of sine x. Okay, so what's the duality of sine x?
Cosine x.
Cosine x, okay. So 1 plus sine square x. And then you times cosine x. Yeah, you got it. Okay, good job. Now it's not that complicated, right? Once you break it down step by step, okay? Now this one over here, we have an integral of this continuous function. However, both upper and lower limit, both are function of x. It's not a constant. So how can I differentiate this with respect to x? Any idea?
Multiplication.
We break it into 2 parts, okay? Break it into 2 parts. So we need to have, so let's break it into 2 parts. Break it into, split them, okay? Split into, okay? So because you need the constant, right? Okay. So how about we let the constant to be 0? So in between them, okay? So, okay. So it will be from 1 minus 2x to 0. Okay, and then here from 0 to 1 plus 2x. Remember the property of integral, right? If you have a continuous function from that to that, you can break it into 2 separate parts. Okay, so this to 0, 0 to this, then that the sum of these two integral will be the same as from this to this. Okay. So let's do that. So you can also use 1. Okay, 1 will also work. Okay. Okay. Now we got to this. Now the second one is good because it's an integral here from constant to a function of x. But this one here, the constant is up here. You need to put them down here. So we need to switch the upper and lower limit here. So we need to switch that upper and lower limit and put a minus sign in front. So this will be from 0 to 1 minus 2x. T sine dt. Okay, now we're ready to differentiate this. Okay, so when we differentiate this with respect to x, everyone tell me what do I get? So we have this minus sign in front, right? Now we just need to replace the, what do we replace? Replace the t over here, right? Replace the t over here by 1 minus 2x, okay? So we have 1 minus 2x times sine of 1 minus 2x. But this is not all. By the chain rule, okay, by the chain rule, we have to times this by the derivative of this right here, this function. This is a function of x. So what's the derivative of this with respect to x?
-2.
-2, right? So need to times -2. Let's put it over here. So we times -2, okay? Because if I put it in the back, it looks like -2 times this, okay? So I like to put it in front. So times -2, okay? Okay, done with this one. Then plus, it's similar. We differentiate this. So we replace this t here by 1 plus 2x. By the chain rule, we have to multiply this by the derivative of this 1 plus 2x, which is 2. So put a 2 in front, okay? All right, so finally, this part over here, you just need to, so for this part over here, so you just replace this by 2, and that will be the answer, okay? So 2 times this plus 2 times this, okay? And you can just leave your answer like this. The sign of 1 minus 2x and sign of 1 plus 2x, they're not the same. You cannot combine them, okay? Okay, are you guys good? Fundamental Theorem of Calculus part 1, okay? Do you get a feel of this? Okay, give me a thumbs up if you guys here. You guys here? Okay, good. All right, I might take a road this way. Okay, right, I see you. Okay, now this is part 1, okay? So that's Fundamental Theorem of Calculus part 1, okay? I saw you. Okay, so now, okay, what happened over here, it is, so when you integrate a continuous function from a to b, when you integrate that function from a to x and differentiate that with respect to x, you get back to the same, you get back the same function f, right? Okay. So I'm going to research, so remember this integral of the function f here, when you integrate that function from a to x, you get a new function g of x, and we think about it as the area under the curve, right? From a to x, right? So that was the area so far function. So that's g of x, okay? So that is g of x. So that's the area so far function. That's g of x, okay? Okay. Okay, so, wait, hold on. And what happened, according to this Fundamental Theorem of Calculus part 1, and then when you differentiate that with respect to x, we get back to the same function that you integrate with, which is this f over here. So, which means that g here is an antiderivative of this function f. G is an antiderivative function f. F is the derivative of g. G is an antiderivative of f. It's like father and son, son and father, you know, this is the relation to reverse, right? Okay. So G is an antiderivative of f right here, okay? So when you integrate this function from a to b, that's the same as subtracting this integral over here from a to a, right? Okay. Now this one over here, okay, think about it in terms of this picture here. So remember the g here, you can interpret that as a function, as the area under the curve, okay, from a to x. So this over here will be the area under the curve here from a to b, okay? So that's g of b, okay? That's g of b over here, okay? Now, what about this? This one over here, I know is equal to 0, right? It's equal to 0. The upper and lower limit are the same. So when the x over here is the same as a, then the area under the curve will be 0, right? But it's also called g of a, right? G of a will be the area so far, right? From a to a. Okay, so that's g of a right here. So it's going to be g of b minus g of a. Okay, you think about that as the area under the curve. Okay, so it will be g of b minus g of a, where g is an antiderivative of this function f right here. Okay, so when you integrate that, you can find an antiderivative of this function f, and then you subtract. Well, it doesn't have to be this function g. It could be any other antiderivative of this function. Okay, so because any antiderivative of this function over here is they're going to be different by a constant. So when you subtract them, the constant are going to be subtract out, right? So it doesn't matter. Okay, so I will put an antiderivative, the small f here. I put it as big F. So big FB minus big FA. Okay, so this. And this is the Fundamental Theorem of Calculus part 2. Okay, so what does it say? So it says that if this function is continuous on a to b, when you integrate this function from a to b, you just need to find an antiderivative of this small f function. Let's call that big F. And then evaluate at the upper limit b, subtracting this big F here, evaluate at the lower limit a. Okay. Okay. So let's try to understand this in physical terms. Okay. Now this is the velocity function of an object. Okay. When you integrate this velocity function, okay, and the time here from a to b, okay, then what happened? Well, that will be equal to an antiderivative of this function, right? So antiderivative velocity function is position function, SOT. So let's put S over here. So S. So S over here is its position function, which is an antiderivative of the velocity function, right? And then you're going to evaluate this function at the upper limit, which is b, and then subtracting this position function here, evaluate at the time a. So that is SB minus SA. Well, which makes sense, right? This integral over here, remember that when you integrate the velocity function, okay, remember the area under the velocity curve, it is the distance traveled, okay? The area under the velocity curve is the distance traveled from time A to time B. So that corresponds to the distance traveled. Well, the distance traveled from A to B is a change in the position right here, okay? So that's SB minus SA. So yeah, so that will try to think about it. So SB minus SA, so that's the distance traveled, okay? Okay, now let's do more examples just to get a feel of this. So I'm integrating this function, okay? This is a continuous on all number from 1 to 3. So all I have to do is to find an antiderivative of this function. What's an antiderivative of this function over here? Can you find an antiderivative of this function?
Yeah,
E to the x.
E to the x?
E to the x.
You got it. So it's e to the x. And then we just need to evaluate this function from 1 to 3. So that will be equal to e to the third power. And then subtracting
E to the 1.
e to the first power. Yes, you got it. Okay. So which is this EQ minus E, right? Okay. Now some of you say, how come you don't put a plus C here? Antiderivative is, most general antiderivative is e to the x plus c, right? Notice that if you do that, what happened here is that the constant here are going to be subtract out, giving you the same answer that you got over here. So really doesn't matter you put a plus c or not. So for simplicity, we don't put a plus c over here. So just put e to the x right there, okay? Okay, now some notation. So this notation here means FB minus FA. Substitute B in, subtracting, substitute A in, okay? Or you can use this notation or this notation. They all mean the same thing, okay? Okay, number 2. We're trying to find the area under the curve, okay, from 0 to 1. So here's the curve, okay? So this area under the curve from 0 to 1 will be this, this shaded area right there, okay? So let's set up an integral. So it will be the integral of what function? X squared function, right? Okay, dx. X go from where to where? What are the upper and lower limit here?
0 to 1.
0 and 1, right? 0 here to 1, x go from 0 to 1. Now, that corresponds to this area under this curve from 0 to 1. Okay, so that's this integral here. So we just need to find an antiderivative of this function. Can you think about? So an antiderivative. What's an antiderivative of x?
1/3 x to the 3rd power.
Yes, you got it. Okay. So that is x to the 3rd power. Remember the exponent increased by 1 when you take antiderivative, right? And then divide by that exponent, divide by 3. Okay. And then you're going to evaluate this. X here go from 0 to 1. So that will be 1/3 minus 0, which is this 1/3. So the area under the curve from 0 to 1 will be 1/3 over here. Okay. Okay, now if you somehow get stuck over here, I do with you over here. Okay. Remember when you differentiate x to the n, that's n times x to the n minus 1. Now when you find antiderivative, okay, then exponent over here is going to increase by 1. So we have x to the m plus 1, and then divide by m plus 1 over here. Okay, so that will be an antideuty of this x to the m. Okay, so remember the process here. Okay, question? Okay, let's try this. Okay, so this integral here is continued on 3 to 6. So let's find an antideuty of this function. What's an antideuty of 1 over x? On
ln
that's your log.
absolute value of x.
Yes, very good. And you remember the absolute value. That's great. Okay, you need the absolute value. Okay. Now we just need to substitute the upper and lower limit in, right? So we will have ln of 6. Okay, ln of 6. Subtract ln of 3. Okay, which you could simplify this. Okay, remember when you have the difference of 2 ln, so you can write it as ln of the quotient, right? 6 divided by 3. 6 divided by 3 is 2. So this is ln of 2. Okay, so this integral equal ln of 2. You can think about that as the area under the curve from 3 to 6. Okay. Okay, now the next one here. Find the area under the cosine curve from 0 to b, where b is between 0 and power 2. Okay, so think about this b over here, between 0 and power 2. So this area, okay, from 0 to b, correspond to this integral. What integral? Can you help me to find the integral?
Negative sine x. Wait. Integral. Is it from 0 to
B.
0
Yeah,
to b. You got it. 0 to b. Okay, what's the function?
Cosine of x.
Cosine x. You got it. And then dx, right? Okay, very good. Now we just need to find an antideuty of this, right? What's the antideuty of this?
negative sine x? Right.
Wait,
Sin x.
sine x? Yes, sine x.
Yep.
Yeah, it's sine x. Remember, be very careful with this, okay? So when you find antideuty, you have to think about what function differentiate will give you this. The deuty of sine x is cosine x. So this is the y one, okay? And now we substitute the upper and lower limit here. So we have sine of b minus sine of 0. What's sine of 0?
0.
Sine of 0 equals 0. Very good. Okay. So this is just equal to sine of b. So kind of interesting, right? So we have a cosine curve from 0 to power 2. Then the area under the curve right here is actually sine. Under this cosine curve, the area under the curve here is a sine. It's sine of b. Okay. So this is cosine of b, the coordinate over here for this one. The area here is this sine b. Okay, it's interesting observation. Okay. Okay. Yeah, so some of you might got stuck over a little bit confused about this antideuty things. Okay. Remember, see, when you differentiate sine of x, you get cosine x. So when you find antideuty of cosine x, so you go backward, so that is sine of x. So remember, antideuty of cosine x is sine x. Okay. Okay. So another interesting observation here is when the b here it is power 2. So the area under the curve here is sine of power 2, which is 1. So this area under the curve, under the cosine curve from 0 to the power 2 is actually equal to 1. Very nice number, 1. Okay. Okay. Now we put the two parts of the fundamental theorem of calculus together. Okay. So the first part says that if you have a continuous function on a to b, when you integrate that function from a constant from a to x, and then later on differentiate that with respect to x, you get back the same function f that you start with. Okay. Part 2 says that if you integrate this continuous function f here from a to b, that's equal to any antiderivative of the small f function. Okay. Evaluate at the upper limit, subtracting that antiderivative, evaluate at the lower limit over here. So you can write it this way: f of x, x go from a to b. Okay, so that those are the two parts of the fundamental theorem of calculus. So basically, it says that differentiation and integration are inverse process. So each undoes what the other does. So they cancel. Okay. Okay. Now, let's not stop right here. Okay. Question? Okay. Now, over here, you find an antiderivative of the small f function, and then you evaluate this from a to b, right? So this stands for an antiderivative of this small f function. So notice that from a to b here, from a to b over here. How about we take away from a to b? If I want a notation for an antiderivative of the small f function, then I can just take away this a to b over here. So I will use this symbol here to stand for an antiderivative of the small f function. Okay, so this is called an indefinite integral because you don't have this upper and lower limit here specified. So it's called indefinite integral. And that stands for antiderivative of the small f function. Okay. So for example, okay, if you have this one without the upper and lower limit here, this stands for antiderivative of this x squared. So antiderivative x squared will be x cubed over 3. Because we're talking about the most general antiderivative, right? So you press C. So don't forget to press C. So if you have this integral here, so press C over here. Okay. So which is it's a family of function. It's a function, a family of function. C here is an arbitrary constant, right? Okay. Now what happens if you put the upper and lower limit over here? If you put the upper and lower limit here, it's called an indefinite integral. So upper and lower limit are defined. Okay. So we did it before, and this is equal to 1/3, and which is a number. This number here, think about that as an area under this curve from 0 to 1. So it's 1/3. It's a number. Okay. So without this upper and lower limit here, it's a family of function. With the upper and lower limit here, this is a number. Okay. Think about that in terms of area. Okay. So we're done for section 5.3. I was supposed to stop here. However, I decided to add one more page to help you, just to help you to, like, in case you get confused with the process here. So differentiation and integration are inverse processes. Okay, so let's try to do this together. Okay, so when you differentiate cosine x, what do you get over here?
Sine x. Oh, negative sine x, right?
Yes, negative, don't forget. When you differentiate that, you get negative sine x. Okay. Now, what happens if you integrate cosine x? So what do you get? So you find the antiderivative of x.
Sine.
Right, you got it. So it is sine x. And because there's motion antiderivative, so don't forget to press a constant. Okay, so press C. Okay. Now what about this? Okay, this one. Okay, differentiate sine x. What do you get?
Cosine x.
You get cosine x. And you integrate sine x. What do you get? which means
Negative
what?
cosine plus c.
You got it. Okay. So when you use cosine x, the derivative of cosine x is negative sine x. And because this one doesn't have a negative sign, so you fix this by putting the negative sign in front. Okay. So don't forget the negative sign over here in front. Okay, and then plus c. Okay. So the process over here is, so you think. So what function, when you differentiate, give you that? So when you differentiate cosine x, and you have this negative sign over here, the derivative of cosine x is negative sine x.
Yep.
So they'll cancel and give you sine x over here. Okay. 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 Last one. What happens when you differentiate a constant k? K here is a constant. What do you get?
1,
Hold on.
0.
0.
You get 0. Okay. You get 0. Okay. That was an easy one. Okay. Yeah. Sometimes the easy one was the one who easy to make mistake. Okay. So that's now what happens when you integrate a constant? What do you get?
That's
Constant
K.
times x.
X. Yeah.
K times x. Don't forget what?
Plus C.
Plus
C.
c.
Yes.
Oh, yeah.
Don't forget to press C. Okay. So you think. So when you differentiate kx over here, that's equal to k, right? Okay. All right. So now I review this. So I actually put them side by side. So then you can to distinguish between them. Okay. So the lesson ended. I'm going to post this on the notes on Canvas. Do you need more time to copy down the note? Okay. I'm going to stop share now. Okay. I'm going to post it.